10 minutes without hitting the record button. Find point on y equals to 2 minus x closest to the origin. So this is in-class example 5.3.6 on page 162. So there's a similar problem, like I think at the last homework problem in this week's homework set, it's like this. So I thought it would be kind for me to work something similar, so you're not just, out in the dark. So these problems are actually really, really fun to set up and to think through. So y equals 2 minus x. Well, that is a line with y-intercept 2 and slope minus 1. So that's what we're dealing with. We're looking at that line, right? And then the question is, if you pick a point on the line, like x comma y, you're trying to what? You're trying to minimize the distance to the origin, all right? Minimize the distance to the origin. So I'll make a picture. That's this distance right here, right? I can't. I'm trying to make a straight dot, 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 dot. So, fun fact. For d greater than 0, let's see here, minimizing, I think, or maximizing d squared also minimizes d. I can prove that if you'd like. It's kind of intuitively obvious, but if you think about how the derivative, let's say that, if we think about the derivative with respect to d squared or the derivative with respect to d, how are they going to be related? Well, d is an unfortunate letter. Maybe I should, instead of using d, let me use s. Otherwise, just for the sake of not confusing differentiation. You could use L if you like. I mean, L for length would be a good choice here. But check this out. So if ddx of s squared is what? It is 2s ds dx, right? So what does that say? Now here, s is positive, right? So what this means, guys, is that the sign of s squared's derivative is going to match the sign sign of s's derivative, right? So if you think about the first derivative test, they're going to have the same sign chart, like where one is increasing, the other is increasing, where one is decreasing, the other is decreasing. Okay, so that means that like the optimization we could either do for the direct problem this is stated, which is minimize the distance, or we can do it for s squared. And let me show you why. Why would we want to? So you choose. You choose. Here, choose. Like, what's the formula for s? S is the square root of x squared plus y squared. That's the distance to the origin, right? From that point. Versus what? S squared is the square root of x squared. Excuse me, it's x squared plus y squared, right? And for the sake of not writing s squared a bunch of times, let's just call this thing f. Or let's call it, I don't know, the thing we're trying to optimize, I'll call it f, just to give it a name. So which one do you guys want to do calculus on? I want to do calculus on the one without the square root, right?
That is a 5, right?
Hmm?
That is a 5. Right?
Those are all s's. There's no 5 here. My 5 looks like this. Yeah, sorry.
So you replace this for the d.
Yeah, because I was going to talk about ddx, and I'd be writing ddx of d squared, and then 2d of dd over dx, and I don't know, it's just tacky. Okay, so guys, we need to optimize s squared, right? So you're like, optimize f, right? That's our goal. In this case, we're trying to minimize it, right? In this case. Now, what's the trouble with f? Look at this. Oh, wait a minute. Two variables, right? Two independent variables. Well, are they independent, though? Well, no, right? What else do we know? What are we doing? We're trying to find the closest point on the line, right? So y is not arbitrary. It's given by 2 minus x. So what we should do is we should look at f equals to x squared plus 2 minus x squared. So we put in the formula for the curve that we're trying to find the point close to. Does that make sense? Okay, now we have our function to optimize. How do we optimize it? Well, we use calculus. So you take the derivative of it, look for critical points. df dx, what's that? It is 2x plus 2 times 2 minus x times minus 1, right, by the chain rule? That minus 1 is from the derivative of 2 minus x, which gives me minus 1. We can simplify this, right? We get minus minus, which is plus. It looks like we got a 4x. And what? Minus 4? That equals to 0 tells me there's one critical number. It is x equals to 1. Now we should check, is that going to give us a minimum? Now I don't want to find intervals of increase and decrease here. I'm just interested in the question, is it a minimum? So easy thing to do, take a second derivative. I can use a second derivative test then to verify it's a minimum. Second derivative test gives me 4, which is greater than 0, which tells me that f of 1 is local min by second derivative test, right? So there you have it, the closest point. The closest point is what? It is when x is equal to 1. So let's finish it. If x equals to 1 and y is equal to 2 minus x, that's equal to 2 minus 1, which is equal to 1. Therefore, 1 comma 1 is closest point. All right? Now, my question to you is, did you need calculus to solve this problem, actually? How do you find the closest point to a line for a point off the line? What do you do? Do you remember from geometry how to solve this problem? We do what? In geometry, we look at the perpendicular bisector to the line, right? And if you did that, it looks like this, right? So the perpendicular bisector between the origin and the line is going to give you the closest point. And it just so happens that when you look at a line with slope 1, which is perpendicular to a line with slope minus 1, the intersection point is 1, 1. So that's another way we could solve this problem without calculus, just with, methods of high school geometry. However, I don't think the one I've given you in your homework set you can solve with geometry. I think the one in your homework set you have to solve with, actually, did the one in the homework set I give you a line, or did I give you a curve? Remember? I don't remember right offhand. So any questions about this one?
Let me.
I will foolishly attempt the other problem. I thought I saw the other student in this class here before class. I don't know where he went. 5.3.7. Maybe I saw somebody else. I don't know. Same page. This one is 3 minus x squared. Point on. To the point 1, 1, 1. To the point 1, 1. So again, any questions about the first example? I'm going to do one more example, and then we'll do the lab, okay? I shortened the lab, so it should take less time, hopefully. Last year I had this litany of questions, and at the end of it all, I was just like, why did I put so many questions in this lab? I could have done just as well with a fewer questions. So I took that advice to heart, and I made the lab shorter. I'm hoping, though, that this conversation here helps you with that last problem in your homework, yeah? So I still need to write your last homework, don't I? But are you guys already done with the homework I've given you? So I'm not holding you up, right?
Tomorrow, right?
Yeah, I'll do it tomorrow. So here's the next problem. Same page of the notes, actually. Find the closest point on y equals 3 minus x squared to the point 1, 1. See, the setup is going to be a little bit different here, all right? So here we go. 3 minus x squared looks like this, right? It's got y-intercept of 3, and it opens down. It's a parabola, right? Now, I don't know if 1, 1... Well, let's see. What are the... I can tell you in a second here. This is root 3, right? And this is minus root 3. That's the x-intercepts. So the picture actually is something like... It's in here somewhere, you know? This is the 1, 1 point. So we're trying to find a formula for like the distance from this point, 1, 1, to an arbitrary point, x comma y, on the curve. All right? How do you find what's the distance formula for one point to another? You guys know that, right? So this time we'll say we're trying to minimize f equal to x minus 1 squared plus y minus 1 squared. See, this is the distance squared. Distance from 1, 1 to xy squared. And remember, like we talked about in the last example, if we minimize the squared distance, we're going to minimize the distance. So let's minimize the squared distance as to avoid annoying square roots in our calculation. Question? Just still absorbing it? Okay. So so the last example was in some sense easier because the point we were trying to find, the closest point on the line was the origin, right? In contrast, this one is the point 1, 1. So that's what makes this different. That's why we have, last time we had x squared plus y squared, now we've got x minus 1 squared, y plus y minus 1 squared, because that's the distance to that point from xy. We're trying to make that smallest. But what do we know? We also know that the point y isn't just any point. It's that y coordinate. It's the coordinate of a pair, x comma y, which is on the graph. What is this graph? Well, this graph is y equals to 3 minus x squared, right? So I can substitute in 3 minus x squared for y, right? Now we have a function of one variable. We know how to do calculus for one variable, right? This is calculus 1, which is the first course in calculus, but it might also be called single variable calculus, because that's what we do in here, single variable calculus. Okay, we also do single variable calculus in calculus 2. That ruins my story, doesn't it? If we did 2 variable calculus in calculus 2, then I'd have a point. But we actually do 2 variable calculus in calculus 3, truth be told. So x minus 1 squared, and this is what? Looks like 2 minus x squared squared, right? Now, you got choices. You could FOIL these out, then do the calculus, or you can leave it as is and do the calculus. I think a lot of times with these sorts of problems, leaving as is and doing the calculus gives you better results at the next stage. I mean, you can do it either way, but we need to, now we're trying to minimize this, right? Minimize it. So we're going to look for critical numbers, right? Where f prime of x equals to 0. So we need to calculate f prime. F prime of x is 2 times x minus 1 plus 2 times 2 minus x squared times minus 2x by the chain rule. Now, there's a hint. I gave us a hint in this problem because the algebra here is a bit of a mess. Let me blow up my hint. I said hint, 4x cubed minus 6x minus 2 factors in this way. All right, so I think I'm going to multiply this stuff out here. So I've got 2 times minus x squared times minus 2x. That gives me 4x cubed is the leading term. In terms of x squared here, there is no x squared term. I've got 2x here, and I've got another 4. I think I have plus 6x. Oh, wait a minute. No, that's 2 times 2 times minus 2. That's minus 6. Minus 6 plus 2 is 4x. Minus 4x, rather, if I didn't make a mistake. Uh-oh. Oh, that does not bode well. That hint makes me worried. Well, I may have to ignore the hint. I'm afraid that hint is not helpful. That's a little bit disconcerting. Could you guys check my derivative? Does that make sense to you? We do 2 times x minus 1 squared. So that gives me that. 2 times 2 minus x squared. So then I multiply the derivative of the inside, which gives you it's minus 2x. All right, well, let me just keep plodding along here. So I got 2x, 2 times, oh, I'm an idiot. What's 2? I'm just stupid. Look at this. What is 2 times 2 times 2 equal to? 8 minus 8. Minus 8 plus 2 is? Minus 6. Aha! There it is. So it was supposed to be minus 6. So thank you to whoever wrote this hint. Sorry, I'm just being silly. Then what else do we got? So I've taken care of the x's and the x cubed. The only thing left is the minus 2. So now you could expand that out in a couple lines if you want. That's how I do it. I just look for terms. f4x cubed minus 6x minus 2. And then helpful hint from the notes, this is factoring as x plus 1 times 2x. What? How? Nah. That ain't right. Like, this is not right, because I don't have a leading coefficient of 4. So let's see here. Is minus 1 a solution to this? Let's check that. Does minus 1, is f prime of minus 1 equal to 0? That's minus 4 plus 6 minus 2. Indeed, minus 1 is a solution. That means that at least this much is true. X plus 1 is a factor. So probably the notes are just a typo. It's probably just supposed to be 4x squared, right? We've got to put a minus 2 over here. And then you can think about what has to go in the middle. See, I've got a 4x squared from here. So I have to put minus 4x here. Otherwise, I would get an x squared term, which I don't have above. See, this 4x squared has to cancel. That's an x. This 4x squared has to cancel with this minus 4x squared because there is no x squared term up here. And that's the only way our x squareds can appear. That forces me to put a minus 4 there, just like I was forced to put a minus 2 here. I think that's it. Let me just check the x's. I've got minus 2x and, oh man. Oh, wait a minute. I can't do math. Minus 2x and minus 4x, which is minus 6x. All right. All is well. Does this factor? How about this? Let's check the discriminant. B squared minus 4ac equals what? So here, a equals 4, b equals minus 4, c equals minus 2. Remember, we can check if a quadratic factors by looking at the discriminant. If it's negative, that means it doesn't factor. So here, this is 16 plus what? Well, I'll do it. Minus 4 times 4 That's times minus 2. Looks like that's, what is it? 32. Uh-oh. That means this factors. So how are we going to factor it?
The answer would be negative 16.
Negative 16. Why would...
4 times 4 is 16 times 2, 32, 16 minus 32.
But that's not a minus because I got a minus and a minus. You see, I got 2 of them.
So it'd be 48.
It'd be, oh man, is that as far as it goes? Yeah, it is. There's a stopper there. Well, yeah, you're right. It would be 48. Thanks. But the larger point, of course, here is it's positive, which means we can factor it. All right? So how do you guys want to factor this? Tell you what, I'll do it. So I've got 4x squared minus 4x minus 2. So this is 4 times x squared minus x minus 1/2, which is 4 times x minus 1/2 squared minus 1/4. And of course that's minus 2/4. So that's minus 3/4. So I'm completing the square, which is, of course, 4 times x minus 1/2 minus the square root of 3 over 2 times x minus 1/2 plus the square root of 3 over 2. All right? So in summary, we get critical numbers c equals minus 1, c2 is equal to 1/2, plus the square root of 3 over 2, and C3 rather, is 1/2 minus the square root of 3 over 2. I believe, if I haven't made a silly mistake. I mean, let me just double check here. Oh, come on. Don't you do that to me. Go away. I don't care about your extension. What was the quadratic I was trying to solve? It was 4x squared, right? Minus 4x or plus 4x? Minus 4x, and that was the constant term? Plus what? Oh, minus 2. So, what are you doing? That never happens. This is why you should never teach with technology. It's a fool's errand. All right, finally. So, yep. Okay, so that's what we found. So we have 3 critical numbers here, right? 3 critical numbers. These are my critical numbers from the algebra I just erased. And how do I decide which one's a min, which one's a max? How about this? We take f prime prime of x, what do we get? We get 12x squared minus 6, right? So let's check. What is f prime prime of minus 1? What is f prime prime of 1 plus the square root of 3 over 2? And what's f prime prime of 1 minus the square root of 3 over 2? So first of all, 12x squared minus 6 gives me what? 12 minus 6, which gives me 6. It's greater than 0, so that's a minimum, a local minimum, right? how about when I plug in 1 plus root 3 over 2? So we do what? I'm supposed to calculate 12 times the square of the critical number and then add 6, right? What? Worthless. All right. So 1 plus, you could use your calculator if you want, right? 1 plus square root of 3 divided by 2. We're supposed to square all that. And then do what? Add 6? Or subtract 6? I can't remember. Minus 6? All right. So this gives us, as it turns out, about 16.4. So that's also a local min, right? And how about the other one? Put a minus there instead, right?
Yes, sir.
And that gives about minus 4.39. So what does that say? That's less than 0, right? That's a local max. Oh man, we got 2 answers. How do we decide which point is closest? So let me just explain to you. Okay, so there's various approaches you could take here. I'm going to take a geometric approach, all right, partly to avoid a bunch of numerics. But so our graph looks something like this, right? The point 1, 1 is like in here somewhere. Well, it's probably more like here, right? So there is over here at minus 1 some point that if I drew my parabola right, that is like, let's see here, 1 plus the square root of 3 over 2. That's what? What is this, 1 plus square root of 3 over 2? What is that in terms of a decimal? What, 2.7 something divided by 2, so it's about 1.36 or so. So that's like, that's here somewhere. That's like here. Minus 1 is over there, right? So the point on the parabola over minus 1 or the point on the parabola at 1 plus root 3 over 2, which one's going to be closer to 1, 1? It's pretty obvious, right? The local minimum we're looking for is this one. So the closest point on the parabola to 1, 1 is 1 plus root 3 over 2. That's my x value. What's the y value? Well, I plug that in, right? 3 minus parentheses 1 plus root 3 over 2 squared. So that should give me the closest point on the parabola to the point 1, 1. So the analysis here was more difficult, right? Because the formula is kind of complicated, but don't get lost in the details. Basically, when you do the calculus, if you get more than one critical number, then you have to decide amongst them which is the one that's actually the answer you're interested in, right? And hopefully you have physical reasons or geometric reasons for knowing that there should exist an answer, right? I mean, that's a presupposition of the method, that there's an answer to find, right? Now you might wonder, like, what does that local maximum mean? What's 1 minus root 3 over 2 anyway? I think 1 minus root 3, so root 3 is like 1.717. So this is probably the point that's like here-ish, you know? So of the points that are close in this sense, that's the furthest point away. Does that make sense? Like that point right there is this 1 minus root 3 over 2. It's kind of the furthest point away if you're just looking close to here. So like locally, that's the furthest point away. And something similar happens with minus 1 in terms of it being the closest point. Well, at minus 1, if you get over to minus 1 and look at the points close to minus 1, well, there's at minus 1, that's the closest point for the points on the parabola close to there, right? So this can happen. It'll pick up local, I mean, calculus will pick up local maxes, local mins, but you get a finite list of them, and basically the same logic as the closed set test, the closed interval test. We pick a winner and loser. But this time we have to pick winners and losers from a little bit more than just plugging in the number. I mean, yeah, we could plug the numbers. We could have just plugged these numbers into the f function and seen which one was smallest, you know? And it would have given us this one as the smallest. Excuse me, that one as the smallest value, because that one is actually the closest, right? But I don't need to do that because I can draw the graph and think through it, you know? You could just plug the numbers into f and see which one's biggest and smallest just the same, but that's also legitimate. I just am avoiding that because it's pain. All right, enough. Enough. So there's some more help with your homework. We should start the lab since everybody's here. So I'll get into it. So we're talking about Taylor polynomials today, all right? And let me just tell you what a Taylor polynomial is again. Taylor polynomials, if you have a function which is smooth, meaning that you can differentiate it as many times as you like, all right? So if f is smooth, meaning that f prime, f prime prime, f prime prime, prime, etc., all exist, all right, near x equals to a, then the kth order Taylor polynomial centered at a is this. It is f of a plus f prime of a times x minus a. What's that? These first two terms. Do you recognize them? What's that? If I put y equals to that, what is it? Oh, I'm sorry, I put the camera right in your line of sight. So I do the constant plus the slope. So this has point a comma f of a, and it's got slope f prime of a. If we put y equals to this, we're looking at the tangent line. So this is what we call the linearization of the function centered at a earlier in the course. But it doesn't stop there. Taylor polynomials keep going. So the next thing is 1/2 f prime prime of a times x minus a squared. And then next, you got 1/3 factorial f prime 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 of a times x minus a cubed. All right? Cubed. And then it keeps going until we get to, well, let me check on my notation. I think I put a k here. Yeah. So 1/k factorial, you do the kth derivative evaluated at a times x minus a to the power k. So this is the kth, trying to see if my, I think, stupid camera's got stuff in the way. I can't tell if it's actually getting this or not. But anyway, this is the kth Taylor polynomial centered at a. If you put a equals to 0, then it looks like this, right? It's a little bit easier because you just have, powers of x. So let me just work out a specific example for you, just to try to make it a little less mysterious before we start the lab. So here's an example. We could look at the f of x, I don't know, cosine x. All right? And we could try to, let's try to find the Taylor polynomial for cosine centered at 0. All right? And what we won't do TTK. We'll do like T, I don't know, 6 should be enough. T6 of x with a equals to 0, okay? So what does that mean? That means we need to figure out derivatives of cosine all the way up to order 6. But that's easy, right? That's easy. See, because we have f of x is cosine x, right? What's f prime? Minus sine, right? What's f prime prime? What's the derivative of sine? The derivative of sine is cosine, but there's a minus. So we got what? Minus cosine x. What's f prime prime? Or f3? Minus sine, right? So minus gives me sine, right? Then f4, oh look, we're back where we started, right? And then it just keeps doing this. It just keeps doing this cycle of answers as you keep differentiating. It's always these. But the next one is minus sine x, and then you've got the sixth derivative, which is minus cosine x. All right, so now that we've calculated the derivatives, we need to evaluate them at a. We have to plug in a to figure out the coefficients of T6. This is just like the tangent line. You differentiate, but then you have to plug in the point of tangency to find out the slope, right? So, as I recall test 1, there's some of you who haven't quite come to terms with what I just said. But anyway, f of 0 is 1. F prime of 0 is sine of 0, which is 0. Right? Sine of 0 is 0. So the ones with sine are going to be 0. The ones with cosine, they're going to be plus or minus 1. F prime prime of 0, minus 1. F3, 0. F4, fourth derivative evaluated at 0 is cosine of 0, which is 1. The fifth derivative evaluated at 0 is 0. The sixth derivative evaluated at 0 is minus 1. So this is what we get, 1, 0, minus 1, 1, 0, minus 1. All right? So what that tells me then, that tells me everything I need to know to write down the Taylor polynomial for cosine, right? And what is it? Well, so I'll write it here, T6 of x is going to be f of 0 plus 1/2 f prime prime of 0 times x squared plus 1 over 4 factorial f4 of 0 times x to the 4th plus 1 over 6 factorial, the sixth derivative evaluated at 0 times x to the 6th. That's going to be T6 of x, the sixth Taylor polynomial. Okay, truth is it's the seventh because 0 is also a Taylor polynomial, but you guys wouldn't have noticed if I hadn't said something. Why did I say something? Man. So why didn't I write the other terms? Well, the other terms, the odd terms, they're all 0. Fun fact, the Taylor polynomial of an even function centered at 0 only has even powers. The Taylor polynomial of an odd function, if it's centered at 0, only has odd powers. So, like the evenness and oddness is reflected in the Taylor polynomial, which is kind of neat. So what do you got here? You got 1 minus 1/2 x squared plus 1 over, 4 factorial, by the way, guys, is 4 times 3 times 2 times 1, also known as 24. What was f4? Well, it was 1, right? So plus 1 24th x to the 4th. 6 factorial is 6 times 5 times 4 factorial, which is 30 times 24, which is a big number. That's 600 plus 4 times 30, 720. So 1 over 720, x to the 6th. And there you go. This is a sixth order approximation for cosine, which will do very, very well at approximating cosine close to 0. You can try it out. for example, try this out. Let's see, like, what's T6 of 0.1? What's that going to be equal to? 1 minus 0.5 times what? 0.01, right? Plus 1 over 24 times 0.1 to the fourth, plus 1 over 720 times 0.1 to the sixth power, right? We could calculate that if I had my calculator. Ah, yowzers. So what do I got? 1 minus 0.5 times 0.01 plus 0.1 to the fourth divided by 24 minus 0.1. If my fat fingers can make through this, will be amazing. 0.1 to the sixth divided by 720. So if I haven't made a stupid mistake, that works out to, according to my handy-dandy Casio 115 ES, 0.99500411653. And you can contrast that to if you just take the cosine, right? And should we use cosine degrees or cosine radians here? Which would be appropriate? Which mode should I be in? Degrees or radians? What do you think? Radians. Radians, we always do calculus in radians. So radians, because in radians, the radian sine derivative is cosine. The degree function sine's derivative is not cosine. It's got a scale factor for degrees. It's like you have to divide or multiply by 180. It's messed up. But anyway, here cosine in radians of 0.1 is what? Check it out, folks. It is 0.99500411653. Wow. So to the limits of my calculator's accuracy, the sixth order approximation for cosine exactly reproduces the value of cosine as produced by the calculator. That's how good this approximation is, because we're pretty close to its center, right? If we just used, if we didn't have the sixth order piece and we just used up to the fourth order, we'd have some error here. If we just use 1, we'd be a little bit off, right? Actually, cosine of theta equals to 1 is a pretty good approximation for cosine close to 0. But even if you just use these first two terms, like 1 minus x squared, that gives us a very good approximation for cosine close to 0. That's what the Taylor polynomial does. Taylor polynomial takes a function, right, and it replaces it with a polynomial, right? And if you think about computer science, coding polynomials is pretty simple, right? Because polynomial formulas are a process of a finite number of additions, multiplications, and powers. All of these things can be easily implemented on a computer. And in contrast, what's sine? How do you put sine on a computer? How do you put cosine on a computer, right? Well, this is actually how you do it. You write an algorithm which replaces sine or cosine with their Taylor polynomial, and that allows you to generate values of sine or cosine to whatever accuracy that you need. Something like this is actually how it's done. So now the full theory of Taylor series and all that stuff, that's in calculus too, but this is where we'll start. So, open up your lab and have at it. That's pretty much all I got to tell you today. So I will shut up and I'll just try to help you guys, if that sounds good. So like next week, I'll go over what's called Taylor's theorem. Taylor's theorem will show us how far off the Taylor polynomial is from the function. It gives us a specific bound on the error. Interestingly, in terms of the next derivative we don't use. So that's what next week's lab is about describing the error in the Taylor approximations.